Hello. Got a few of the guys here. Oh, yeah. One of our girls, two of our girls, three of our girls. Okay. People are joining in. Right. That is 11 of us. Somebody's got the smooth jazz playing. Maybe Aiden over there. Yeah. Is that that might have been. All right. Okay. You may or may not have noticed that I am at school. I'm actually coming at you from our classroom right now. That's our posters on the wall and all of that good stuff. So we won't be interrupted by my daughters unless they made the long drive over here. So it's going to be hopefully a fun, interesting, informative day. Although I was in a meeting with my department chair for the last little bit, and I didn't prepare as much as I wanted to. What section are we on? Did we just do 5.7 day 2? Have we done that one?
No, we're on.
I think we're
That's
on.
what we're on today.
That's what we're on today, 5.7 day 2. Okay, let's see. I'm gonna just hope that I printed that one out, and let's yes. That's what we did yesterday, 5.71. Continue the compounded PE to the RT business. And almost there. Effective rates we did not do, we decided against doing, and here we are. 11, no. Okay, didn't print out. No big deal. I will pull it up on the computer and we can work from there. So give me 1 second. This was unit 10. Yeah. 5.7 day 2. Okay, got it. You know what? I am not interested in 5.7 day 2. These present value formulas, it is nothing that we do in the honors class. You do learn it again in pre-calculus. I think it would be worth our while to skip that. And so let's see what 5.8. Yes, okay. So 5.8 day 1 is where I want to be. Let me go back to Zoom. So we are skipping the rest of that 5.7 stuff. I will do a screen, and I think that looks like it. So hopefully you have something which looks a little like this. Okay, that equation at the top is one of the 2 equations that I will expect you to memorize. It looks slightly different than the form that I've seen it before, that I've shown to you before, but that is okay. It really is the same equation. Here they're saying that the amount at any time is equal to a sub 0, pronounced a naught, and that really means the initial amount times e to the kt. You can think of that as a equals pe to the kt if you prefer, where instead of a naught, I'm writing a p for principal amount. So I just change it out for a p instead of an a naught. It shouldn't make any difference. Okay, so let's look down at that first example where it says P of t equals 700 e to the 0.03 t. So the initial number of insects Well, that is where A naught goes. What number is where A naught goes, or where P goes? What number do you see there?
700.
700, absolutely. 700. So my initial number of insects is just 700. That rate is that thing right up there by the T. That is that 0.03 is that growth rate. And now we actually have to do a little bit of work in order to find the population after 5 days. And all I have to do is plug in that 5. So into my calculator, I'm going to put 700 e to the 0.15. Which of course, I got that 0.15 times the 0.03 times 5. And I have a myriad of these calculators here today. So if I type in 700 e to the 0.15, and when I hit E on these things, it automatically knew that I wanted to do a power of E, so it gave me that little E caret. If I type that in and hit enter, it tells me I have 813.28. So I'll just put approximately 813 buggies. So far, so good?
Mr. Reeves?
Yeah, Owen.
So when you say one of the two equations that we need to memorize, was the other equation A equals P e to the RT?
No, that is the same equation. They're just calling A naught P and K R. Those two equations are identical. The other one is the compound interest formula.
Oh, the A equals P times 1 plus R over N, that one?
Yeah.
Okay.
Those are the only two formulas. Can you see it on the board? Is that visible? Those are the only two formulas which I will require that you guys know. The trick, of course, is knowing when to use them. The bottom line is unless you're dealing with compound interest, you're using PE to the RT. Okay, so I'm going to use that equation again for part D. This time they tell me the population is 1,000. Still started at 700 and times e to the 0.03 times t. I'm going to divide both sides by 700. Let's see. So I'm going to get 1,000 over 700, which I guess is just 10 over 7, equals e to the 0.3 t. Well, my variable is in the exponent, so I'm going to take the natural log of both sides. The natural log of 10/7 is the natural log of e to some power. Oh, well, that's just that power, 0.3 t. And my answer is the natural log of 10/7 all over 0.3. And again, I can plug that into my calculator and get some sort of approximation here. The natural log of 10 divided by 7. I'm going to hit enter there, and I'm going to divide that by 0.3, and I get, that doesn't look good. Oh, I should have divided by 0.03, excuse me. Natural point, I lost the 0 in there somewhere. 0.0, 0.0. Let's try that one again. Of 10 divided by 7, enter, divided by 0.03, and now I'm getting 11.8 days, 11.9 days. And what is the doubling time for the population? So I'm going to put in a step which I won't often do. I'm going to say, oh, well, if I started at 700, double is 1,400 equals 700 e to the 0.03 t. the first thing I'm going to do is divide by 700, and I'm going to get that 2 equals e to the 0.03 t. Now, most of the time, I won't write this first step. If you're doubling, it doesn't matter where you started, it's the same amount of time. So I will usually just skip right to that step. And then I can say the natural log of 2 equals 0.03 t. And my answer is t equals the natural log of 2 over 0.03. And my calculator will give me an approximation. And about 23 days. 20. All stuff which is very pertinent. Population growth includes population of people infected by viruses. Definitely these are the types of equations that people are using to predict how many people are going to be infected and whatnot tomorrow.
Mr. Reeves, can I see your D? Can you just explain that to me again?
Sure. The question was, how long will it take the population to reach 1,000? So I set the population to be 1,000, and I just solved for t. I divided by 700. 1,000 divided by 700 is 10/7. I took the natural log of both sides, because the natural log of e to something is just that something, and then I divided by 0.03.
Okay, thank you.
No problem. I don't have the full view of you guys. Do I have everyone here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So I'm really just missing Darcy, of course, who we are sending these recordings to. So does everyone want to take a moment, unmute themselves, and say hi, Darcy?
Hi, Darcy.
Hi.
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 That was sweet. Okay. Colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells and t is the number of hours, express n as a function of t. Well, n equals that original amount, whatever it happens to be, e to the k, some people would call it an r. You might want to mute yourself again, whoever that was.
Mr. Reeves, we can't really see the.
You can't
Thank
see. Let me also scroll this down. So I'm on the right problem here, and can you guys? I got to get back to a view of myself. Right there.
Is it a little zero on the bottom? Is that just like a, what is that?
That's telling you that that is the initial number. N naught is how it's pronounced. And of course, that we have a good reason for doing that. What's the good reason? Why
not?
Why not? We have a good reason for doing it. Why? Why not? So glad I recorded that joke. Okay, if the number of bacteria doubles in 3.5 hours, so I'm going to say that 2 equals e to the k times 3.5. Okay. Where did n naught go?
You divide it?
I divided it out, sure. Technically on the left, I should have 2 n naught, and on the right, I should have 1 n naught. And when I divide both sides by n naught, they just go away. So from here, I can figure out what k is. So I'm going to say that the natural log of 2 equals 3.5k. And I'm going to say that k must therefore equal the natural log of 2 over 3.5. Okay, and there is the exact value.
What does not represent?
When I say not, that means the initial condition. So n naught is the initial number.
Wait, Mr. Reeves, I'm still a little bit confused about like how you got rid of the N.
And not? Okay, sure. Let's put
Yeah.
in the unnecessary step. Let me just write this down real quick. K is approximately 2.0 or 0.20. With a little bit of rounding in there. So if it doubles in 3.5 hours, so then I would say 2 times my original amount equals my original amount, e to the k times 3.5. But to go from here to here, I just divide by n naught, and those go away.
Wait, so why is in the first equation it's just n, and then in the second one it's n naught?
You lost me.
Like for the equation in A, you just
Mhm.
wrote n equals, but in the equation in B, you wrote n naught equals.
Because they told me that specifically it doubled. So if I had an amount, which I'm calling n naught, which could be 10, it could be 5, it could be 100 million, then after 3.5 hours, I have double that. So if
Okay.
n naught were 5, this would be 2 times 5, it would be 10. If n naught were 10, this would be 20. And if this were 100 million, this would be 200 million. But it doesn't matter once I divide it out. In part C, tripling is a hard question to answer. We're going to do it. Quadrupling, though, is a very easy question to answer. How long does it take to quadruple?
4.
0.4.
Oh.
You know it takes 3.5
Oh,
hours
yeah.
to double. If I double twice, I've quadrupled. So I know my answer for how long it takes to triple will be somewhere between these two. Let's do it. Let's say that
Mr.
3.
Reeves,
Yes,
can we see the equation for the quadruple after that too? Is that okay?
I'm doing it right now. For
okay.
quadruple, sure if you
Yeah.
want. 3 equals e to the k t, where k is approximately 0.20. I'm going to say the natural log of 3 equals k t, and the time to triple should be natural log of 3 over k equals t. So I'm going to plug that into the calculator, but since I already have what k is in the calculator, what I'm going to do is I'm going to hit natural log of 3 divided by answer. Okay, so I'm not retyping.
How did you divide by the answer?
I hit divided by, and you'll notice over here above the negative sign, there's answer.
Yeah.
Okay. And I got about 5.55.
Can you show the formula for this one again?
Mm-hmm. Okay.
So why do you use k as 0.2 here?
Because that's the k that we found in part B.
Okay.
K doesn't change. Okay, now someone asked me to do it for quadrupling. It's the exact same thing, only this time I'm going to write 4 equals e to the kt. I'm going to write that the natural log of 4 equals kt. I'm going to write that the natural log of 4 over k equals t. However, I'm going to go to the exact value for a natural log of for k here. So I'm going to say that that is natural log of 4 over natural log of 2 all times 3.5 equals t. Sorry, it's hard to hold the camera here. Someone came in and took all the document cameras out of all the classrooms. Well, the natural log of 4 over the natural log of 2 is the log base 2 of 4. It is just 2. So this is 3.5 times 2, so it equals 7. But again, that's something that you should be able to do without having to write down any equations.
But if you were to plug the natural log of 4 over k equals t into a calculator where k is 0.2, you find that in B.
You would get the 7.
Okay.
Wait, I'm confused with that part right there after you went from like ln4 over k equals t, the next step.
Okay.
You
What I
get
did was
30.
plug in the exact value for k. Remember, k is approximately 0.2, but is exactly natural log of 2 over 3.5.
Oh, okay.
So I plugged that in because I didn't need a calculator to do what the natural log of 4 divided by the natural log of 2 is.
Okay.
So if you basically, when you're finding out whether it's like triple or quadruple or something, you just put however many it's by, whether it's 3 or 4 at the beginning, equals e to the kt.
Technically, there's a step above these where I would say 3 times n naught equals n naught e to the kt. But what disappears from both sides? N naught. So nobody ever writes that. It takes the same amount of time to go from 1 to 100 as it does to go from 100 to 10,000. From 10,000 to 10 million. Or I guess a million. Yeah, a million. Sorry. Okay. The only reason that this was exponential growth instead of exponential decay was because of k, that rate. If that rate is a positive number, this thing will grow. If that k is a negative number, on the other hand, this thing will shrink, or the technical word is this thing will decay. This is not another equation. It is the same equation, just the value of k is different. Let's see a problem for this. Okay, all radioactive substances have a specific half-life. A half-life is how long it takes for half of it to disappear. Just like everything that grows takes a specific amount of time to double. We're not saying that if I do 2 half-lives, I'd be down to 0. If I did 2 half-lives, I'd be down to a quarter of what I started with. All living organisms contain 2 types of carbon. There is carbon in the atmosphere. You are constantly breathing in carbon-12, which is stable, and carbon-14, which is technically radioactive. Okay, there are a lot of radioactive things out there which aren't harmful. Carbon-14 is one of them. It has a half-life of 5,600 years, meaning if I had 100 grams of carbon-14 right now, if I could wait for 5,600 years, I'd have 50 grams. When an organism is alive, the ratio of carbon-12 to carbon-14 is constant. When an organism dies, on the other hand, it quits breathing things in and breathing things out. And so the amount of carbon-14 is only going to decrease. This is called carbon dating. This is how we figure out how old certain fossils or certain organic material is. It had to be breathing in order to do this. A fossilized leaf, which I guess doesn't breathe, but you know probably better than I about the exchange of oxygen and carbon dioxide that plants go through, contains 6% of its normal amount of carbon-14. If the half-life of carbon-14 is still 5,600 years, how old is the fossil? Just once, I'm going to put in that unnecessary step. I'm going to say that we started with 100% of the normal carbon-14 equals e to the kt, and we are left with 6%. So when I divide, I end up with that 0.06 equals e to the kt. Now, the bad news is I don't know. What was that?
Can you show us, please?
Nope, so sorry. Forgetting you guys can't see. So nobody writes this step. They just go straight to that one. My goal here is to figure out how old the fossil is. I want to solve for T, but as of yet, I don't know what K is. So what I'm going to do is I'm going to say that 1/2 equals E to the K times 5,600, just like that. I know that no matter how much I start off with, after 5,600 years, I'm left with half of whatever I started with. So I can solve this for K. I'm going to take the natural log of both sides. Natural log of 1/2 equals 5,600 K, and divide by 5,600. Natural log of 1/2 divided by 5,600 equals K. Again, my calculator can give me a pretty good approximation for that. Natural log of 0.5, all divided by 5,600 is 0.00012, negative, I should say. K equals a negative 0.00012. I could have predicted that it was going to be negative because this is exponential decay.
How were you able to take like the original equation of 0.06 equals e to the kt and then turn that into 1/2?
Okay, so what I did, this isn't representing the same case. This is representing after an unknown amount of time. This is representing after a very specific amount of time, that 5,600 years. So this is true for all carbon-14 everywhere. This is what it means to have a half-life of 5,600.
Okay.
That must be true. So now that I've have a working value for K, I can plug it back in and solve for T here. So the natural log of 0.06 equals KT, and the natural log of 0.06 divided by K equals T. I'm going to do that without hitting the clear button, without typing in negative 0.00012. I'm going to go over here and hit natural log of 0.06 divided by my answer, just like I did before. And I am going to get a rather large number here. T is approximately 22,729 years. Now, admittedly, they go 0.80, blah, 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 but radioactive dating is not that accurate. This is probably, in terms of significant figures, like way too many. So I'm just going to leave it like this. Just to be clear, after how many years would I be down to 50% of my carbon-14?
5,600.
Great. After a little more than 11,000 years, I'd be down to half of that. I'd be down to 25%. Okay. After another 5,600 years, so roughly 1,800 years at this point, I'd be down to 12.5. And after another 5,600, I'd be down to 6.25. So this seems to be in the right ballpark, this answer. Okay, same kind of equation here. I don't know, let's see how much further we have to go. We just have this one more that we're gonna finish up today. So let me switch over the computer screen for those of you who don't have it in front of you. That was this last problem, and here is our final problem. I'll give you guys a moment or two to work on it on your own. At the same time, I'm going to be working on it here, and then we can compare notes. See people still working away. Looks like we got maybe about a quarter of you guys are finished. Did we get an answer? I got some no's. Anyone yes? I got a yes. Okay, what time are we administering this next dose?
3:45.
3:45 is what I got here. All right, nice. So 3:45. I said 1, which is the amount of milligrams which need to be present when I give the next dose, equals 10e to the negative 0.4 t, just using their equation, plugging in 10 for that original amount. I divided both sides by 10. I took the natural log of both sides. I divided by negative 0.4, and I plugged into the calculator and got about 5.8-ish. They said to the nearest quarter hour, so 5.8 is really close to 5 3/4 of an hour, and 5 3/4 of an hour after 3:40, after 10 is 3:45.
Can I see the LN step, please?
Yep. There's the whole shooting match for you, really. Oh, and we can hear you texting or emailing or whatever.
Sorry.
No problem.
I teach.
Yeah, I don't mind. It's just we're all listening to it going shrook.
Oh, sorry.
Okay. So there it was. I'm glad that we were able to not do that 5.7 day 2 stuff. That gives us a little bit more leeway on reviewing and things like that. But are there any other questions before we call it? I'm getting a no. All right. Tomorrow is Friday. We are meeting. I presumably will be back at my house. We have a weekend. We've got we X on Tuesday, I believe. Does that sound right? Okay. And I think I put online when our test is. It's
The
coming up.
2-day test on Thursday and Friday.
There it is. Okay, 2-day test. All right. We'll get some practice up before then, and I will see you guys tomorrow. Looks like maybe a question?
Yeah.
Yeah, what's up?
Is the test, like, is it going to be like one part word problem and one part like other stuff from the unit?
I think
or
it's going
like
to be one part calculator, one part non-calculator.
Oh, okay. Got it.
All right.
Can I see the last part of the equation quickly? Thank you. Yeah, thank you.
Okie dokie. Well then, thank you guys for joining me, and I will see you tomorrow.
Thank you.
You bet. Have a good one. And bye, Darcy.
Thank you.
You bet.
Mr. Reeves,
Yeah. Oh, yeah.
when we reach,
I think, look, I kind of made a decision on this, and that is that I don't want to punish myself. So I'm not going to make you guys do it. Thank you for being, diligent about keeping on me, and B, of course, being willing to do that. But I'm just going to assume that you guys are whatever I would have come up with, you would have done well on. So I'm going to give you credit for it. I wouldn't expect this on a normal basis, of course, but all of us are just overwhelmed, and I'm not going to punish myself by giving myself more work and making this thing up. So does that seem okay to you guys? I would imagine that's got to be a yes.
yeah, great, thank you.
All right, Awesome.
Yeah.
Thank you for keeping diligent on that.
I do just have one quick question on the problem we did.
Yes.
Why are you putting 1 equals and then all of that?
Because in the problem it says the second injection must be administered when there is 1 milligram of drug present. So
Okay.
I set it equal to 1 to figure out when there would be 1 present.
Oh, okay.
Okay.
Oh, for the time when it would be.
Yes.
Got it.
All right. I will catch up with you.
See you tomorrow.
You bet. Bye.
Thank you.